Hello everyone and welcome in the fourth lecture of Vibration with MATLAB. In this session, we will discuss Newmark beta method to solve the single degree of freedom system. This is my system where I am having a mass connected with a spring and a damper. In case of force vibration, I have to apply a harmonic force, or for the free vibration, I will give some initial displacement or velocity to my system to exhibit the free vibration. This is the governing equation for the given system mx double dot plus cx dot plus kx. On the right hand side, if there will be force, it will be for the force vibration case, otherwise it will be 0. And I am interested to find the response of this system. What do you mean by the response? Response means I am interested to get the displacement, velocity and the acceleration of my system for different times. For example, I am interested to find the value of this displacement for t plus delta t plus 2 delta t and so on. And what is this delta t? Delta t is the time step. What are you doing exactly? If you will see the governing equation, it is a second order ordinary differential equation and it is an initial value problem. That means you want to get the response in the time domain, and for that you need to give some initial boundary conditions. Initial boundary conditions means you have to supply initial displacement and initial velocity to your system so that you will get the response for future time steps. So using any numerical method or analytical method, I can get this response. In last three classes, we have solved the problem of free vibration response of a single degree of freedom system as well as the force vibration response using the state space formulation. State space formulation is a technique which reduces the order of your differential equation, and then we applied the numerical method to get the response. In the current lecture, we are going to apply Newmark method, which is another numerical approximation to get the response of a second order ordinary differential equation. In the current lecture, we will primarily talk about the free vibration. In addition to that, I will also explain you when we are applying the numerical method itself has different approaches. For example, implicit numerical method or explicit numerical method. So in brief, first we will talk implicit and explicit method, then we will see the philosophy of the Newmark method, and then we will see the MATLAB implementation. So in case of free vibration, this would be your governing equation where the right hand side will be 0. As this is initial value problem and the order of the equation is 2, I have to give two boundary conditions in terms of displacement and the velocity. You can get the solution using the analytical approach or the numerical approach. And here I am showing that what exactly you want. You want to calculate the displacement for different time step. For example, this is your initial condition. So this xt is nothing but your x0 which is available to you. You will supply this initial displacement and velocity to your system, and then you will calculate the value corresponding to the next time step, and then using these value you want to calculate the value for the further time steps. So in numerical approach, you have two types. One is the implicit techniques or the explicit techniques. And what is the fundamental difference between implicit and explicit? In case of explicit approach, what you do, you consider the previous time step to get the response for the current time step. For example, my initial condition I am denoting with step t, means I know the data corresponding to time step t and I am interested to find the data corresponding to t plus delta t. So what you will do to get the response for a given time step, you are going to use only data available for the previous time step. So method which use only the previous time step comes under the category of the explicit method. Here I am showing that if you want to find the x value for t plus delta t, you will use your displacement, velocity and acceleration available for the t time step. And here I am showing one random equation, that this is the equation where you want to get the x for t plus delta t using you are using velocity with some constant and the acceleration available at the previous time step. On the other hand, in case of implicit method, in addition to the previous time step, you also consider data for the current time step. Here I am showing example that if you want to calculate the value of t plus delta t, you are going to use the previous values as well as the current value. Now there is a confusion that how we will know the value of the current time step as we are calculating it for the current time step. So what happened in case of implicit method? When you will make the mathematical formulation your equation, ultimately you will get simultaneous equation, and you have to solve this simultaneous equation using some numerical techniques. We are not going to discuss too much detail of explicit and implicit method, but for understanding you should know that what is the fundamental difference between the two method. So here I am listing what is the main difference between implicit and explicit method. In case of implicit method, as your equations are coupled equation, if you want to get the response for t plus delta t, you are having t plus delta t itself in your solution part. So you are having simultaneous equation and you have to solve the simultaneous equation, and for that you have to apply further numerical methods. So that it is mathematically more complicated, you required more effort to solve the equation in the implicit case. On the other hand, for the explicit method, what you do, you solve a particular time step and then you move for the next time step. How I am saying so? As I am saying that if you want to calculate the value at time step t plus delta t, you only need the value available for the previous time step. So you have to only solve this time step. Once you will get the solution for t plus delta t, you will get the solution for t plus 2 delta t using the previous value available. So in case of explicit method, your solution is simple and rapid. But in case of explicit method, your solution is very sensitive with respect to the time step. You have to supply a del t value, and if your del t value is not sufficiently small, your solution will become unstable and you will not get the right value. Your erratic solution will come. On the other hand, implicit methods are unconditionally stable. That means you can use the large time step. So there is a trade-off. Explicit methods are simple and rapid, but we required very small time steps, so we have to give more number of time steps for a given time range. On the other hand, implicit methods are mathematically complicated, but you can give large time step. So directly we cannot differentiate which method will be better. Based on the situation, we can apply either implicit and explicit method. Our Newmark beta method is an implicit method, but there is a condition there, because when you will see the Newmark beta method, you will find there are number of constants given alpha and beta like. So based on the numerical value of those constants, your Newmark beta method may become implicit or explicit. So let's see how your Newmark beta method look like. This is the philosophy of Newmark beta method. This is your equation of motion for the free vibration. It is it is homogeneous second order ordinary differential equation. These are the parameter you want to calculate: displacement, velocity, and the acceleration. What is input value available with you? You know the initial displacement, you know the initial velocity, as well as you have to supply the time step. These are the three equations which we need to solve for the Newmark beta method or Newmark method, please. So these are the three equations, and here I am just telling you that how this equation will look like. First, you have to solve the displacement for the current time step. As t is the previous time step and you are solving it for t plus 1. So your initial value will be corresponding to your t time step, and you are calculating your displacement for t plus 1, and the equation will be function of your previous displacement, velocity, and acceleration, as well as two constant alpha and beta. These two are the numerical constant defined by the Newmark method. Then you have to supply the delta t value. In addition to that, you will need your mass, damping, and stiffness, which are available with you. Once you will solve the first equation, then you will move to the second equation, which is corresponding to the acceleration for the current time step. And for this, you are going to use previous three values. In addition to that, you will also use the current displacement value, and therefore we call that the Newmark method is an implicit method which required solution value from the previous time step as well as the current time step, and alpha, beta and delta t. After solving the acceleration, you will solve the velocity, and velocity will also have acceleration value for the current time step in addition to the acceleration and velocity for the previous time step. So I will show you three equations, but here I just want to explain you that Newmark method is an implicit method, and these are the three equations you have to solve to get your solution for the current t plus 1 time step. Either I will write t plus 1 or t plus delta t, both are same. So here are the equations. The first equation is corresponding to your displacement, which is having mass value, damping value, stiffness value, as well as the displacement for the previous t time step, your velocity and acceleration for the previous time step, as well as here also you are having some displacement, velocity and acceleration. All the values will be available with you, so you will get the displacement, and then you will put this displacement value in the second equation as well as the previously available value, and then you will get the acceleration, and then you will get the velocity. So you have to implement these three equations in your MATLAB code to get the response of your system. Once you will get the value at t plus 1, you will go for the t plus 2, and in case of t plus 2, whatever is written here as t will become the t plus 1. So every time if you want to calculate value for a given ith time step, for example, for a given time step, let's you want to get the solution for the fifth time step. So for the fifth time step, you will use the value of the fourth time step, as well as you will also use some of the value for the fifth time step. And what is the name of this alpha and beta constant? Alpha is known as the Newmark parameter, and the value of alpha varies between 0 to 1 by 4, and it is related to the stability as well as the accuracy of your numerical approximation. So for the given case, I am just taking alpha is equal to 1 by 4. If you are more interested, you can read any textbook, or on internet you can read that how you will select your alpha value. But as I am telling you that it is related to the stability as well as the correctness. Beta is denoted as numerical damping. In our system we are having physical damping that is defined by C, but when we do the numerical approximation, the numerical method itself has some damped effect. That means it can reduce the amplitude of your response, or it can increase the amplitude of your response. For example, if I am taking beta value 1.2, the damping will be minimal. If you will increase the beta value by 1 by 2, you will have a positive damping. That means the amplitude you will receive at the end of your solution will have the damped value. That means it will reduce. On the other end, if the beta value is less than 1 by 2, that means you are going to have a negative damping, and negative damping will increase the amplitude. So in case of beta less than 1 by 2, you are having the diverging solution. In case of beta 1 greater than 1 by 2, you are having a positive damping, so you will get a converging solution. Converging solution means your amplitude will be less than the correct value. So normally for the neutralization we consider the beta value as 1 by 2 in all the cases. In addition to that, if beta is 0, this is very special case. As I said, in case of beta Newmark beta method, the actually method is an implicit method. But if your beta will become 0, the method become explicit method. I'm not detailing that how mathematically it will become the explicit or implicit, but for your information you should know, if my beta is not equal to 0, your method will be implicit. If my beta is equal to 0, your method will become explicit, and it becomes the equal to a central difference method. So I'm not going in the detail of that. So I hope that you have understood the philosophy of the Newmark beta method. You have to apply these three equations in your MATLAB code. The value of alpha we can take as 1 by 4. The value of beta will be 1 by 2. M, C and K are available. I will consider an initial time step, as well as I need initial displacement and initial velocity. Using all these parameters, I will be able to get the response, and for that I am going to make a MATLAB code. So let's see how your MATLAB code will look like. Here I am showing my MATLAB code for beta Newmark method. The first two lines are our standard text which we normally write when you start a MATLAB code: clear and clear, CLC and the clear all. CLC is corresponding to clearing the your display. Clear all will clear your memory. Here I am showing value of M, K and C. That means I am considering a system where my spring is 20, my damper is 0.2 and mass value is 1. All the values are considered in SI unit. Line 6 and 7 are additional line. Line 6 is indicating A, B, E, I, G, K and M. So what is this EIG? EIG is actually solving your eigenvalue problem. This is standard MATLAB function in the MATLAB library, and when you will give input to K and M value, actually you are going to solve the eigenvalue problem, which will give two output: eigenvalue and eigenvector. Your eigenvalue will tell you the natural frequency of your system and eigenvector will tell you mode shape of your system. Since this is a single degree of freedom system, so we are not interested in the mode shape here. But when we will solve the multi degree of freedom system, you can apply the EIG command and that will give you both natural frequencies as well as the different mode shapes. So here I am showing that this A and B will give me mode shape and natural frequency. B is actually going to give you the omega n square value. And in line 7, what I am doing, I am taking square root of this and I am dividing it by 2 pi. So I will get a frequency which will be in hertz. So using these two lines, you will be able to get the natural frequency of your system. Otherwise, what you can do, you can also get the natural frequency by simply doing under root k by m. So I will request you, you can cross check, you can calculate your natural frequency on your calculator using this formula, and then you can cross check that how you are getting the natural frequency using the EIG command. Then line 9 is showing the initial displacement value. So I am giving an initial displacement of 0.01 and my initial velocity is 0. Time 50 is actually showing that I want to get the solution for 50 seconds. dt is my time step, and how I have considered this 0.01. I have already discussed this in my previous lecture, that how to calculate the time step. So again I am not discussing it. Here I am taking my time step as 0.01 second. Line 30 is my actual statement which is calculating the displacement, velocity and acceleration. So the statement indicating that the output of this function named beta Newmark 2. This is my function, and for this I am having a separate .m file which I will show you soon, and the output of this function will be displacement, velocity and acceleration. Input will be your mass, stiffness, damping, time, initial displacement, initial velocity and your time step. So when you will run line 13, the output of this line will be your output response of displacement, velocity and acceleration. This is my function where I am implementing three equations which I have seen for the Newmark beta method. So the first line indicating the function which will give output of displacement, velocity and acceleration. The name of the function is beta Newmark 2, which is your choice. Whatever you will write here, the MATLAB is going to save your file with this name. These are the input value: m, k, c, time, displacement, velocity and time. Please remember here, you can write any variable here. No need to write the same variable, because you will see earlier in the main code we are writing m, k and c as small letters, but here I am writing with the capital letter. Doesn't make any difference, but the order should not change. The first value will be corresponding to the mass, second will be stiffness, then the damping. So you can write here a, b, c, whatever you want to write, but the order will basically going to consider that whatever a will be here is corresponding to small, the b will be corresponding to k and c will be corresponding to the damping value. So whatever variable you want to write here, it is your choice, but the order should be same. Then line 2 is showing my alpha value and the beta value. In the code I am denoting a as my alpha and b as my beta value. I have taken alpha 1 by 6. It is your choice. As I said, you can also take it is 1 by 4. Then line 3 and 4, just I am redefining my initial displacement and initial velocity, and then in line 5 I am calculating my initial acceleration. And why so? If you will see your Newmark equation, the first displacement equation is the function of your displacement of the previous time step, velocity of the previous time step, as well as the acceleration of the previous time step. And what is your input? You have x naught value, so that x naught will be corresponding to this displacement. Velocity you are having, so velocity is corresponding to this value, but you are not having acceleration which is there for the initial time step. So what you can do, you are having your governing equation, that is mx double dot plus cx dot plus kx is equal to 0. In this equation you can put your initial velocity and initial displacement, and you can calculate the initial acceleration. That is what I am doing here. So here, solving this equation, you will get initial acceleration, and then you can use the three equations to get your displacement, acceleration and velocity for next time step. I am using here a for loop. So you will get your response starting from your second time step, because at first time step you are denoting time t is equal to 0. Then your next time step will be 0 plus delta t. Then the next time step 2 delta t. Then 3 delta t. And so on you will solve. So this is the statement for your for loop. Here are the three equations. And when you will run this function, the output will give you your displacement, velocity and the acceleration. Line 14 indicating you are defining time vector for plotting the displacement, velocity and acceleration. So this is just a vector creation which is from 0 to 50 second with an increment of delta t. And line 15 is indicating the plotting command. Here I am plotting time versus velocity. You can change this to displacement, or you can also change it to the acceleration. So this is all about your MATLAB code as well as the philosophy of the Newmark beta method. Now we will see the free vibration response in the MATLAB environment. This is your MATLAB code where I am taking mass value 1 and let's my damping is 0.2, and if I will run my code, this is my response. I am plotting my response, my displacement versus the time. You can see in line 15 I am having x here, that means the output curve is showing displacement on the y-axis and the time on the x-axis. Here you can see the system is a damped system, so that the amplitude is reducing with respect to time, and I am taking my response from 0 to 50 seconds. In addition to that, I have calculated the natural frequency, and you can see that this is your natural frequency which I am plotting in my command window. And why so? If you will see in the code somewhere I have given this semicolon, but here I have not given any semicolon. If you will not give any semicolon here, that value will print in your command window. So I can directly see the natural frequency. Otherwise what you can do, if you would have given a semicolon here, your output will not show anything. Here I am able to see m is equal to 1, and why? Because I have not given any semicolon here. If you will give a semicolon here also, and then again you will run, nothing will come on your command window. And now you have to write this natural frequency value command here, so that you will get the, you can see the natural frequency. So I have to type it and I have to put enter, and I am getting a natural frequency which is 0.7118 hertz. As I said, you can cross check by calculating your k by m value, dividing by the 2 pi. Whether you are getting same value or not, you should check. You can also verify the natural frequency using the graph, because this is a graph between the time versus amplitude. And if I will take the gap between peak to peak value, so let's take this data cursor, put the data cursor on any of the peak here. This is corresponding to a x value 2.81. That means it is corresponding to your time 2.81 second. Then you can take another data point, and for that what you can do, if you simply click the second peak, the first will go away. So what you need to do, you pick the first one and then press alt button and again press, so that you will get the second cursor. Similarly you can take number of cursor on your plot. this is here, then I can have another one. Here you can see that these two peak time gap is 4.23 minus 2.79. So you can take the difference will give you the time period. When you will take the inverse of this time period, you will get this frequency. So this is second exercise. You can cross check your output. Now I'm going to show you that if I will change the mass value or the damping value, how the response will change. So let's increase the damping by 0.4. Now you can see that in the previous case, the amplitude was having a significant value up to this point. But now as I have increased the damping by 2 times, the displacement is almost 0 after 30 seconds. If you will reduce the damping, earlier the damping was 0.2, now let's make it 0.05. You can see that the amplitude has a decay, but very less up to the 50 seconds. So in similar way, you can change the input parameter and you can get the response to understand your system. Similarly, if I will change the mass value, let's increase the mass value to 4. Theoretically, we know that if I am increasing the mass value, my natural frequency will reduce. And if the natural frequency is reducing, the gap between the two peaks should be more. That means if I'll see the response, you can see here that this time gap has increased from the previous value. So I hope that now you are having understanding of the beta Newmark method as well as the philosophy we have considered for the beta Newmark method. So with this note, I am closing this session. Thank you.